Then we looked at circular linked list, that there is beginning and points to previous node. Like in this case, there's the last node point to previous node, and it becomes a circular linked list. Now to distinguish if we're traversing, when do we put an and? Because we keep traversing the link, right link, we would keep going it, or we keep traversing left link, we will keep knowing this, and so we will not know where the end node is or where the list end. So we define the notion of what is called a header node. So header node would have two links, left link and right link. Header node does not contain any information. It just indicates the beginning of the list or end of the list, depending on. So you start from the header, traverse, and you come back to header, you know that you have traversed the list. Doubly linked list also facilitates that you can insert and remove elements both the ends, either beginning or the end, because you are doubly linked, so you can traverse either direction and insert node in either place. So if I have a right link will point to the header here, and then you see this will point to the first node, and similarly left link will point to, if you look at left link will point to this, and this will point to the next node, and this becomes a complete linked list. And that's how things basically continue. So they appear in that order, and that's how the use of header is in a circular list, so that we can identify where does my list begin and where does my list end. I did discuss a question in the class saying, consider a singly linked list. The list may be circular or list may be terminated. We do not know. We do not know the number of nodes. So, and if it is terminating in between, that means there could be possibility that last link could be pointing somewhere in the middle. If last link could be pointing somewhere in the middle, how do we figure out whether the list is terminating or list is circular? Does anyone recollect how do you go and implement it? The solution? I discussed this in quite a detail in the class. Anyone would like to say? Lithis?
Sir?
Madhu? Sir? Yeah, go ahead.
What, sir?
What, sir? The question I asked you. How do we determine whether the linked list is terminating or it is a circular linked list? You can't modify a list. You can't keep something tag a vegetated node. So when I start from the beginning of the node, how do I know that this is terminating or it is the circular list pointing to somewhere in the middle? And I would like to answer. Abhishek. Shruti.
Yes, sir.
Yes, sir. So can you answer the question? How do you figure out?
If the pointer of the last node is null, then it is terminating, sir.
How do you know that this is the last node? Because you are continuing pointing. So how do you know it is the last node?
When the pointer of that last node is null.
But you don't know. If you keep traversing, you don't know if it is circular, it will never be null. So we'll keep going like this.
Yes, sir.
So how do you figure out? The job is over. But how it is a circular work? Because it will keep traversing. You will keep going in the loop forever.
Yes, sir.
I did discuss in the class. Any thoughts?
Oh. Um,
Anybody else? So primary we look at, we basically maintain two traversal pointers, traversal 1 and traversal 2. At one time, traversal 1 traverses only one node and traversal 2 will traverse two nodes. And each time we compare, when we traversal two nodes, we compare, is it my pointer equal to the same as previous traversal with the green node? Because if it is circular, the first is traversing slowly, so at some point here, and the other is faster, so it's going to catch up. Because it's going to catch up, I would notice circular. So when I traverse with the two links, two traversals, one at the double the rate of other ones, sooner or later, if it is circular, will catch up, we'll know. And if terminating, they will terminate anyway. So we'll be able to determine whether the linked list is terminating or whether the linked list is circular. That's the way this program could be implemented and figure out. This is one of the good interview questions that you should probably realize. So we looked at the list, how to represent polynomials. And polynomials, we take an example, consider a polynomial 10x raised to power 4 plus 5x square plus 6x plus 21. And we said when you want to represent this polynomial as a linked list, each node need to keep two pieces of information. One is the coefficient, other is the exponent, which is power. When you do that, basically assign one node for each term, each node point to the next term, and last node, which is basically this node, would point to the null, and each node would have two pieces of information, the coefficient part and the exponent part. So 10x power 4 will point to the next term, which is 5x square. 5x square will point to the term 6x. 6 will point to the term constant 21. And 21, if the coefficient is 21, power would be 0. The 21 x raised to power 0 would basically give me 21. And last node will point to the null. This is how we represent two polynomials. Now, given these representations, we can implement and see. So we define two fields, coefficient and the exponent, and point to the next, and that's how list could be implemented. And then we can declare an object, polynomial 1, polynomial 2, and so on and so forth. And there's a way we could implement our polynomial. Now, given this representation, we can do polynomial operations such as additions. If we need to add two polynomials, represent them as two linked lists, like polynomial 1, polynomial 2, as you can see in the screen. And then when represented, you start traversing it. When you traverse, what do we compare? Do we compare the coefficient or do we compare the exponent?
Exponents. Exponents.
Exponent. So compare the exponent. If exponents are same, add the two coefficient and then put this node to the list. If the sum is not 0, if the coefficients are different, look at whichever one is the higher, put that term into the list and keep moving. We've taken the example, so start both the traversal, compare the coefficient. Since this coefficient is higher, so this exponent x power 6 is higher, so we copy this node into the result sum and move this pointer to the next node. Now this exponent of first term is higher, so we copy that, add it, and move that and compare again. So both of them the same exponent. This time we add it, becomes 9x square. So add, and this way we basically do the polynomial addition, and that's the way addition would work. How we go about doing multiplication of two polynomials? Given this case, given the two polynomials, what approach you would take to multiply two polynomials? Amit, Disha, give a thought and give me answer. Netra, Akash, are you guys there? Looks like simply had joined the class and moved away. Maharaj needed to answer. Karthik, Likhit, nobody. How do you multiply two polynomials? Varun,
So if exponent is same, then we'll multiply the coefficient.
exponent is not same then.
Then
Then
we
also
write
we multiply, sir.
Yeah, so what is the approach you will take? So term by
Take
term, but how
the
do you
first
keep
term
building the
of the
list?
polynomial 1 and multiply to all terms of the polynomial 2. Repeat
Correct.
for the all the first repeat for the terms which are there in first polynomial again. Like that second term
Yeah,
multiplying for
correct.
all
And
terms
then
of
add
the
it.
second.
Perfect. Thank you, Lithis. So basically, take the first term of the polynomial 1, multiply it, so declare result sum as 0, and then take the first term polynomial 1, multiply with all the terms of second polynomial, add it to the sum, take the second term of the first polynomial, multiply with all the terms of second polynomial, add it to the sum, keep repeating, and finally you'll basically get the answer. And that's how you do the multiplication. Then we give example of sparse matrix using linked representation. Here we discuss we need a column header, we need a row header, and then we add the elements. So basically, so essentially the row header and column header would be the same structure, just logically shown differently. We add the elements, and for each row we keep defining the pointers, and we keep defining the pointers, then it becomes much easier for us to track. And once we are done with all the row elements, then we look at the column pointers and calculate. So each one is a, if we look at, each one is a circular linked list to maintain, and this is the row headers, and this is the column header. That's what we do, and draw the diagrams. And you can look at, look at the nodes, what we're doing. And once this is done, once we add all the column elements, all the row elements, then so each time row is complete, we basically make the circular at the last row, but column part, once all the rows are over, then we look at the last element of each column and make a circular linked list for including the column header, and that's essentially what we do. So next we simply define all the column circular part like this, And then you do for each node. So for the column number 1, then we do column number 2. And then we do last column number 3. It makes it basically header there. And that's what we basically do. All the column headers and all the row headers, and that essentially what we basically do. And this way we represent a sparse matrix using linked list representation. It's again a single linked list we represent, and that's what we've done. Some part of questions and the assignment as well. So building all the row headers is what we have done. Then we looked at how can we use linked list to define a stack and the queue, and we taken the example of, let's say 5 elements we need to add to the stack, and we remove the elements. So start with the null stack, then we add a new element, top move, and the next element always point to previous one. Top is always to the last element added, and pointer is in reverse direction, and that we are maintaining a single linked list, and that's how stack is implemented. So if you need to remove an element, we remove that element and move top to the previous element, and that's what basically what we do. This is implementing a stack. Same way we can use linked list to implement two queues. Now we have 2 pointers. One is the front, other is the rear. We start with a node with first node with both front and rear pointing to the same node, and as and when we add elements, we keep moving rear, and rear always point to the last node, and when we need to remove, we basically remove the node pointed to by the front, and that's what we basically do. So if we need to remove, we move the front pointer, and that's how it basically works. So we can use singly linked list to implement both as a stack or a queue. It's quite often queue, but a stack could equally be done. And that was content of module 3. And module 3 we started with trees, and we defined a tree as basically a finite set of nodes, which one of them node is called the root of the tree, and remaining tree are such that all the remaining nodes are partitioned into different set, which define a subtree having their own subtrees, and the root is their subtree. So the recursive definition, as we've seen, and we've taken the example of family tree, our parental trees, the language trees, we've taken those examples. And then we looked at the different terms. So we had the degree of a node, which basically indicate the number of subtrees that node has got. So for the leaf node, since there will be no subtree, so degree of the leaf node would be 0, but degree of other nodes would be how many subtrees that node has got. Nothing, the temporary disturbance, so we should be back. Can you guys hear me?
Yes, sir. Yes, sir.
Hello? Yeah, okay.
Yes, sir, we can hear
Then
you.
we look at define the leaf node, which is the degree 0, because it has no nodes, no subtrees. And in this diagram, we looked at all these nodes, K, L, F, G, M, I, J. These are leaf nodes. And then we define further called parent node. Basically, the node for whom I'm subtree is my parent. Similarly, we define children node, siblings, all the nodes who are same parent is a sibling, and then we define ancestors and descendants, grandparents, grandchildren. These different terms you basically define. So ancestors are all the node starting from the root of the tree to the node, they all become ancestor, and this proper ancestor that does not include the node itself. And having children, siblings, we look at the level of a node, a level of a tree. So typically start root is level 1. Some computer scientists root at level 0 was a matter of convention, but in the book we follow so it's a root at level 1. And then for each children, its level would be level of its parents plus 1. And that is what we can determine. And when you look at the level of a leaf node, that is also called height of the tree. So when you look at the leaf node, whichever the leaf node has the highest level, that will determine the height of the tree. And for this example, we can see that height of this tree is 4 because we have up to 4 levels here. Whether you follow this path, but if I were to add, let's say one more node here, let's say X, then the height would become 5 because we would be traversing 1, 2, 3, 4, 5. So it depends. So we look at the maximum level of a node and that determines height of that tree. Then we looked at binary tree. So binary tree is a tree which is of degree 2. That means each node can have only 2 subtree, and we distinguish between what is called a left subtree and a right subtree. So by formal definition, we can say it is binary tree is a tree with finite set of nodes which consists of a root node and 2 distant binary tree called left subtree and right subtree. And the difference between the binary tree and normal tree is that in binary tree there could be empty tree. Sorry, yeah, but in normal tree there would not be an empty tree there. And then we looked at the binary tree properties, saying basically what is the max number of nodes in the binary tree. So max number of nodes at any level I is 2 raised to power I minus 1, and max number of binary tree would be, if the tree is of height k or depth k, the max number of nodes would be 2 raised to power k minus 1. So I will not go over the proof, and we use a induction approach, proof by induction, proof for the base case, and then take a inductive hypothesis, and using induction step, saying that assuming it is true for the depth k, then we at the level k, we prove for level k plus 1, and that's how we prove the binary tree property. Similarly, we also define the relation between the number of leaf nodes and these two. We said if n0 is the number of leaf nodes and n2 is number of nodes of degree 2, then we proved that n0 is equal to n2 plus 1, and we proved that again using by induction and by the logic. Then we went to define a full binary tree and a complete binary tree. A full binary tree, we basically say each node has 2 subtrees, and all the nodes at the last level have the leaf node with all the same levels. And that's what we see in this case. And we number the nodes in the full binary tree. We then define complete binary tree. So essentially, when you define a full binary tree, that means the total number of nodes in a binary tree is equal to maximum number of possible nodes. If that is the case, that is called a full binary tree. The complete binary tree is binary tree such that when nodes are numbered of this tree, the number would correspond to their numbering in respective full binary tree, and in that sense, that would be binary tree. Like this is a complete binary tree, but if I were to define a node like this, then this is not complete binary tree, because before I can add a right subtree to the node f, I need to have a right subtree to node E, left subtree to node F. Only then I can add this node. And hence, if I do like this, not a complete binary tree, but when I remove this node, then it's complete binary tree. That is what we defined. So essentially, we said complete binary tree define two properties. One is that every level is completely filled except the last level, and nodes are always added to the left side as far as possible. Binary tree. Representing the binary tree, if we represent in an array, it becomes a lot more easier. We can say that we're starting with the root node at location 1. 0 is only as a filler because calculation becomes much easier. So if the node is at I, parent of I would be at location I by 2 with the float ceiling. And if I is equal to 1, it has no parent, so that applicable will not be applicable. Similarly, left child will be at location 2i if 2i is less than n, and right child would be at location 2i plus 1 if 2i plus 1 is less than n. And that is what we basically defined. And we take an example. In this case, take a tree and put the binary representation memory. So we can say this is how the nodes. We can represent this using even a binary tree or a normal tree. But if you represent this representation using normal tree, then we will lot of faults and we will waste a lot of memory. So this array representation works for binary tree, but not really very efficient for a normal tree. There we use linked list. Then we looked at the traversals, and we defined three kinds of traversals. So we said either we can widget left, we can widget right subtree, or widget the node. Widget the node basically means process the information element, and with the assumption that widgeting left subtree would always precede widgeting right subtree. So we are only three combinations possible. LVR, that is widget left, then widget the node, then widget right, then LRV, widget left subtree, widget right subtree, widget the node, then widget left subtree, widget the node, widget left subtree, and these three different orders are known as in-order traversal. LRV, the widget left subtree, widget right subtree is called a post-order traversal, and if you do widget the node first, widget left and widget right is called prefix or pre-order traversal. And each edge is in prone. So when we do expression evaluations, we typically do post-order traversal to evaluate, and that's what typically is used. And we've taken some examples given the tree, perform a pre-order, in-order, or post-order traversal for the given trees. We then did some other binary operations such as copying a tree. We given a binary tree, how do you make a copy of it? You start traversing, create a node, and this could be reversal. Basically, for a given node, create the node, and then create recursively called left subtree, recursively called right subtree, and that way we keep continuing and we'll create basically copy of it. We can compare the two trees for equality. That means number of nodes and the number of nodes in the right subtree should be the same. If I'm able to traverse to left in one, I should be able to do the same on the other. So if both are not able to match, then I know they're equal, otherwise they're not equal. And we look at binary tree can be used for expression evaluation. We typically use post-order traversal to do that. And we say representing a Boolean expression, we can evaluate whether the expression is satisfiable. That means, are there assignment of values which results in expression being true? We looked at also binary tree for the leaf nodes. Since there are no left subtree or right subtree, even though node would have pointer, those would be null and would simply be wasting memory. So can those be used? And said for those nodes, we do not have a left subtree, right subtree. We can use them as the thread pointing to predecessor and successor. So we defined as threads that if my left child is null, then we use the left link as the predecessor. And similarly, if my right child is null, then I use my right link as successor. And that way, my in-order traversal becomes a lot more easier. I can just follow the successor path, and then I'll be able to traverse the whole tree. When we do a threaded representation, we also looked at how to insert a node. There are two cases there. Parent does not have a right child, or parent does have a right child. If it does not have a right child, inserting a node at the right becomes much easier. We need to simply point out the right child and be done with it. But if it is already have a node, then we do some movement. We looked at those, and those are we discussed in the class. Then we move to binary search. Where we said that all the nodes in the left subtree would have a key value less than the parent node, and all the nodes in the right subtree would have key values which is larger than the parent node. So definition wise we said either the binary search tree could be empty. If it is not empty, it satisfies the following property. One is each node has exactly one key, and we assume that all keys in binary subtree are distinct. The keys in the left subtree are smaller than the parent. Keys on the right subtree are greater than the key of the parent. And each of the left subtree and right subtree is also a binary search tree. And that is what we basically discuss. And then we've taken some examples saying, given the 4 nodes, how many possible binary search tree can be there? And we take an example of that this can be represented by a Catalan number, which is defined as 2n Cn by n plus 1. And taking the example of binary search tree having 1 node, 2 nodes, 3 nodes, and 4 nodes, and given all possible combinations of those. Then given an expression, we defined a binary tree as well, applications part. So for a given expression, we have to make sure that the order of this followed. We always evaluate. So given expression, build a binary tree. This is not a binary search tree, but binary tree. When we evaluate using post-order traversal. We look at another application called how to determine height of a binary tree. And height, we said, it is take the height of the left subtree, take the height of a right subtree, and whichever the height is higher, and that will basically give the height of my complete tree. Same logic could be used for number of nodes in binary tree, which is count the number of nodes in the left subtree, count the number of nodes in the right subtree, add them together, add 1 to it, and that will give me number of nodes in binary tree. How to find the smallest node in the binary search tree? We said the smallest node would correspond to, we keep traversing left. As long as we can keep going left, we go there. And the moment my left subtree is null, that means that node will point to the basically called the smallest node. So basically, if my root is null, I return that, or root is left node executes, we basically return node. So we keep traversing, and that means this will become my binary search tree. And if it is not, we'll continue like that. So if either root left is null, that means this is null, that this is my node, I keep traversing, and this gives me the smallest node. And same logic we could use for largest tree. So instead of left, we basically traverse the right, and whichever right we traverse, that becomes my largest node. That's all we discussed in all of our module. So summary, we looked at linked list, we looked at trees, and that the overall discussion we looked at. So please visit, revise, review, and the questions would be basically from both. So if you have any questions, please feel free to ask, or you can always reach out, let me know. Otherwise, I'm done. No questions, we can drop out, and we'll close the end. We can take a break, and we can do the next class at 10 o'clock. If no questions, thank you. Have a good time.
Thank you, sir.
Thank you, sir.
Thank you, sir.